Yes, theory of collisions. So in order to understand the theory of collisions, let us try to understand what is impulse and impulsive force, right? So the product of the force and the time is defined as impulse. What do you mean by this? Now, suppose if this body of mass m is kept at rest on the floor, that is, let's say a frictionless floor, let's say this is the ground, or you can call it as floor. This is a frictionless floor, right? And a force F is applied on this body, but the force is applied for very small duration, that is, it is very small, like in nanoseconds or lesser than nanosecond as well. So let us say the duration is delta t and the force is gone, right? So just the force is applied only for small duration and it is gone, right? So it was at rest initially, and immediately when the force is applied for delta t duration, it got some velocity, let's say v, right? So what is an impulse? So impulse is this force which is acting for a very short duration of time, right? This is defined as force multiplied by delta t, the product of the force and the very short duration of time multiplied by very short duration of time. So this is the product of force into time. Now due to this impulse, that is F into dt, what is happening? There is a change in momentum is happening. Change in momentum means what? In work power energy we have seen the momentum. Momentum means, let us say, change is final minus initial momentum, right? Now what do you mean by final momentum? Final momentum मतलब force immediately लगाने के बाद उसका जो product of mass and velocity है, that is final momentum, minus initial momentum. Initially it was at rest, so therefore it is zero. So this impulse has caused the change in momentum, that is mv minus 0. So this is called as impulse and this force is called as impulsive force. So how you can define the impulsive force? The force has the large magnitude if force has large magnitude and it acts for a short time, or instead of and you can write but it acts for a short time, then such kind of force is called as impulsive force. So this is called as impulsive force, which is the magnitude is very huge. Iska magnitude is huge, large magnitude, and it is only acting for short duration of time. Yes? Yeah. Now, linear impulse. What do you mean by linear impulse? As we have seen the definition of impulse, so linear means the impulse which is acting in only one direction. So suppose, let us say this is an impulsive force which is having a large magnitude and it is acting only for a short duration of time. Only for short duration of time. That is, let's say delta t. And suppose initially before applying this force the block was moving initially with velocity, let's say velocity which is u, that is an initial velocity. After applying the force, the velocity becomes, let's say, v, right? After applying this force, large magnitude for short duration of time. Therefore, linear impulse is defined as the force in that direction multiplied by for time duration delta t, which is equal to change in linear momentum. So what do you mean by change? Final momentum minus initial momentum. So in this case, final momentum is m into v minus initial is m into u. This is f into delta t. So this is the definition of linear impulse. Conservation of linear momentum. Now, in order to study this concept, let us consider two masses m1 and m2. Let us consider two masses, those are m1 and m2, moving with initial velocity of u1 and u2 before collision, and it moves with v1 and v2 after collision. So let me explain what is before collision and after collision scenario. Suppose there are two bodies. Let's say this is m1, which is moving with u1 on the right hand side. There is another body m2, which is also moving on the right hand side with u2. Now let us say suppose u1 is greater than u2. So at one point of time in दोनों का collision होगा. Collision means it is getting, दोनों collide हो रहे हैं, right? m1 and m2. So there will be some deformation here, and this is during collision, right? So let us say after collision, this body m1 moves with v1, this m2 moves with v2. So what does the conservation of linear momentum says? Conservation means linear momentum is conserved. What does it mean by conserved? Means initial momentum of the system means what? Initial means before collision. Collision होने के पहले. So this case is of before collision, right? This is for after collision. So the linear momentum before collision is equal to the linear momentum, or you can say the momentum of the system the final momentum of the system after collision. Final means after collision. So final मतलब collision होने के बाद की बात कर रहा हूँ. Therefore before collision momentum is equal to after collision momentum. That means initial momentum of this system was m1 u1 plus m2 u2 bar is equal to m1 v1 bar plus m2 v2 bar. This concept is called as conservation of linear momentum.
Collisions between different bodies in our daily lives, like the collision between a bat and ball, and the collision between a striker and coins in a game of carom. In the subatomic world, we find collisions between various subatomic particles. For example, a subatomic particle called a neutrino collides with another subatomic particle, a neutron. The neutron disappears and one finds a proton and an electron as products of this collision. In any collision, the linear momentum of the system is conserved. If we consider one-dimensional collision between two bodies, then from Newton's third law of motion, they experience equal and opposite forces, F12 and F21, on each other, such that F12 is the force on the first body due to the second, and F21 is the force on the second body due to the first, and F12 must be equal to minus F21. From Newton's second law of motion, if delta P1 and delta P2 are changes in momenta of the first and second bodies respectively, then force F12 will be equal to delta P1 by delta T, and force F21 will be equal to delta P2 by delta T. Since F12 is equal to minus F21, this implies that delta P1 by delta T is equal to minus delta P2 by delta T. Therefore, delta P1 is equal to minus delta P2, or delta P1 plus delta P2 is equal to 0. Hence, we can say that the total change in momentum during a collision is 0, or we can say that the total momentum of the system is conserved during collisions. There are three different kinds of collisions: elastic collision, inelastic collision, and completely inelastic collision. In a collision, if both the total momentum P and total kinetic energy Ke of the colliding bodies is conserved, then it is an elastic collision. In such a collision, the bodies move separately after the collision and the loss in kinetic energy delta Ke is 0. This implies that there is no loss in kinetic energy. For example, the collision between subatomic particles is an elastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and not the kinetic energy, and the colliding bodies move separately after the collision, then the collision is called an inelastic collision. There is some loss in kinetic energy of the system during this collision. This implies that delta Ke is not equal to 0. For example, the collision between billiard balls is an inelastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and the total kinetic energy is not conserved, and the bodies stick together after the collision, then it is a perfectly inelastic collision. There is a maximum loss of kinetic energy during this collision. This implies that delta Ke is maximum. For example, the collision between a clay ball and a metallic ball is a perfectly inelastic collision. Consider a head-on collision, that is, one in which the velocities of the bodies before and after the collision are along the same straight line. The mass of the first body is m1 and is moving towards right with velocity u1. the mass of the second body is m2 and is also moving towards the right with velocity u2 such that the two bodies are moving along the same straight line. If u1 is greater than u2, then there will be a collision between the two bodies. Let the collision between the two bodies be elastic, which implies that it is a completely elastic collision. Let the velocity of m1 be v1 and that of m2 be v2 just after the elastic collision. Since the momentum is conserved, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. On rearranging the terms and simplifying, we get m1 into u1 minus v1 is equal to m2 into v2 minus u2. Let this be equation 1. Since the total kinetic energy is also conserved in an elastic collision, we have half m1u1 square plus half m2u2 square is equal to half m1v1 square plus half m2v2 square, or m1u1 square plus m2u2 square is equal to m1v1 square plus m2v2 square. On rearranging the terms and simplifying, we get m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. On further simplifying, we get m1 into u1 minus v1 into u1 plus v1 equal to m2 into v2 minus u2 into u2 plus v2. Let this be equation 2. Now, dividing equation 2 by equation 1 and simplifying. We get u1 plus v1 minus u2 is equal to v2. Let this be equation 3. Substituting value of v2 from equation 3 in equation 1 and simplifying as shown. We get final velocity of m1 as v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Let this be equation 4. From equation 3, we get v1 is equal to v2 plus u2 minus u1. Let this be equation 5. Substituting the value of v1 from equation 5 in equation 1 and simplifying as shown, we get final velocity of m2 as v2 is equal to m2 minus m1 by m2 plus m1 into u2 plus 2m1 by m2 plus m1 into u1. Let this be equation 6. As a special case, if we assume that m2 was at rest before the collision, then u2 will be 0 and v1 reduces to v1 is equal to m1 minus m2 by m1 plus m2 into u1. Let this be equation 7. And v2 is equal to 2m1 by m2 plus m1 into u1. Let this be equation 8. Moreover, in this case, if m1 is equal to m2, say equal to m, then we get v1 is equal to 0 and also v2 equal to u1. Thus, we see that the two bodies exchange their velocities after the collision. If m1 is much greater than m2, then we neglect m2 in equations 7 and 8. Thus, we get v1 from equation 7 equal to u1. And also, we obtain v2 from equation 8 equal to 2u1. Therefore, in such a case, we see that m1 continues to move with the same velocity as it had before the collision. Whereas, m2 now acquired double the initial velocity of that of m1. In a real-life situation, we do not encounter collisions where bodies before and after colliding move along the same straight path. They collide in two dimensions, as usually observed in a game of billiards or carom. Consider an elastic collision in two dimensions, where a body of mass m1 with velocity u1 along the x-axis collides elastically with a body of mass m2 at rest. This implies that the velocity of m2 before collision, u2, is 0. Just after the collision, m1 moves away with velocity v1, making a positive angle alpha with the x-axis, and m2 moves away with velocity v2, making a negative angle beta with the x-axis. Since the collision is elastic, the total momentum and total kinetic energy of the system must be conserved for the bodies. The law of conservation of momentum must be applied both along the x-axis as well as the y-axis. v1 cos alpha and v2 cos beta are the components of v1 and v2 respectively along the x-axis. Hence, according to the law of conservation of momentum applied along the x-axis, we get m1u1 plus m2u2 is equal to m1v1 cos alpha plus m2v2 cos beta. And on simplifying, we get m1u1 is equal to m1v1 cos alpha plus m2v2 cos beta. Let this be equation 9. V1 sine alpha and minus V2 sine beta are the components of V1 and V2 along the positive y-axis and the negative y-axis respectively. Hence, according to the law of conservation of momentum applied along the y-axis, we get m1u1 plus m2u2 is equal to m1v1 sine alpha minus m2v2 sine beta. As the initial velocities of the two bodies along the y-axis are 0, we get 0 on the left side of the equation. And thus, we get 0 is equal to m1v1 sine alpha minus m2v2 sine beta. On further simplification, we get m2v2 sine beta is equal to m1v1 sine alpha. Let this be equation 10. Since the total kinetic energy is also conserved in an elastic collision, and as u2 is 0, we have half m1u1 square is equal to half m1v1 square plus half m2v2 square. On simplifying, we get m1 into u1 minus v1 into u1 plus v1 is equal to m2v2 square. Let this be equation 11. The total quantities among the three equations are m1, m2, u1, alpha, beta, v1 and v2. Thus, there are 7 quantities and 3 equations. By knowing the values of m1, m2, u1 and at least one among alpha or beta, we can determine the values of v1 and v2. Now, consider a head-on collision, that is, one in which the velocities of the bodies before and after the collision are along the same straight line. That is, a one-dimensional collision. A body of mass m1 moving with velocity u1 collides with another body of mass m2 moving with velocity u2 in the same direction along the same straight line. Let the collision between m1 and m2 be completely inelastic. As the collision is completely inelastic, they stick together after the collision and move with a common velocity v. Since the momentum of the system is conserved during the collision, we have m1u1 plus m2u2 is equal to m1 plus m2 into v. This implies that the velocity after the collision v is equal to m1u1 plus m2u2 divided by m1 plus m2. Let this be equation 12. The loss in kinetic energy of the system, delta KE, is equal to the kinetic energy before the collision minus the kinetic energy after the collision, which is half m1u1 square plus half m2u2 square minus half into m1 plus m2 into v square. We substitute the expression for the common velocity v from equation 12 in the expression for delta KE and simplify as shown. For convenience, we mark two expressions, A and B, and simplify them separately as shown. Thus, the loss in kinetic energy in a completely inelastic collision is as shown on further simplification. As half m1 m2 by m1 plus m2 into the square of u1 minus u2. Let this be equation 13. In case the second body of mass m2 is at rest before the collision, we have u2 is equal to 0 and then the loss in kinetic energy is equal to half m1 m2 u1 square by m1 plus m2.